Hello, and welcome to this video on power supply technologies used for resistance welding. To begin with, let me start by sharing the screen so you can follow along with the PowerPoint that I'm going to use. My name is Girish Kelkar, and I am a welding consultant operating as WJM Technologies. Additional information about my consulting business is on the web at welding-consultant.com. In this video, we're going to review the 4 different power supply technologies that are available for resistance welding processes. And those are alternating current or AC, direct current or DC, high frequency inverter, and capacitor discharge or CD. To the right, I'm showing a schematic, which is a time diagram for the welding process. When the electrodes come together and apply a certain amount of force, after a certain wait time called squeeze time, the energy is supplied where the current flows through the parts and the heat is generated. At the end of the cycle, there is a small wait time called the hold time, and the electrodes are released and you have a welded part. These technologies can be divided into small scale and large scale. That the distinction is kind of arbitrary. So about less than 5 kiloamps would define as small scale, where the applications are a little bit different, the metallurgies are different, the size and shapes are different, and that's why it becomes a separate market. Here we have applications for medical devices, battery tabs, solar cells, and so on. The large scale, which tend to be more structural, and that's for automotive and aerospace and structural applications, where the current can be of the order of 5 to 50 kiloamps, but typically in the range of 20 to 30 kiloamps. On this screen, I'm going to show you control and monitoring options. This is a schematic layout of the setup, which includes the power supply, the transformer, and the weld head. The power supply takes energy from the wall, manipulates it, regulates it, rectifies it, and sends it to the transformer. The transformer amplifies the current and lowers the voltage. And the energy then goes through the secondary, goes through the electrodes, goes through the parts, through the bottom electrode, and comes back to the transformer. So in these processes, you want to control the energy so that you know exactly what you are getting. And there are different ways of controlling. In the high frequency inverter, the control can be done on the primary side. So you can actually control on the primary side in some power supplies, not all of them, in some of them. And there you can produce a very fast rise time in the secondary side. So if you need a very fast rise time, you may have to look at a power supply which does that. Both HF and DC, high frequency and DC power supplies, always offer secondary control, where you are actually monitoring, measuring the current in the secondary side, giving the feedback to the power supply so it can keep regulating, so it can follow the exact profile that you have set up. AC power supplies can be open loop or secondary control. When it says open loop, that means the AC power supply supplies a certain number of cycles at a different tap setting, but doesn't specifically control exactly how much current or energy is in the secondary loop. And so that's why it can be open loop, or you can have a secondary control where you have a coil and you measure the current and provide feedback. The CD power supplies, the cap discharge power supplies, are always open loop. So you are sending the energy, but you are not directly controlling it. You're approximately controlling the time and overall energy, but not specifically controlling the current or voltage. Keep in mind that all power supplies can be monitored on the secondary side. So no matter what you have from the power supply, you can have either a built-in monitor in the power supply, or you can actually buy an independent monitor, so you know exactly what it is providing for recording purposes as well as quality checks. Capacitor discharge power supply is perhaps the oldest technology. It is very simple. It has a bank of capacitors where the charge is stored. And as a user, you will program watt seconds, the energy which can be stored. And then that energy is discharged through a secondary transformer and delivered to the electrodes. The control in terms of time is also quite basic. You have choices between short, medium, and long. And some power supplies, they also might have an extra short, but you have to check with your unit. But typically there are 3 levels. The short for the small scale stuff typically is in the range of 2 to 3 milliseconds. Medium can be about 10 milliseconds, and long can be about 20 milliseconds. Again, every unit is slightly different. So best to measure and to check with the manual for that information. One of the benefits of cap discharge power supplies is that the energy or the welding is not affected by line voltage fluctuations. Since it is a stored energy power supply, it first stores energy and then fires. So the line voltage fluctuations do not affect welding. Also, in many cases, the capacitor discharge power supply is a single phase from the wall. So you can set it up in practically anywhere in the manufacturing plant and do some welding. Especially on the smaller units, the power supply and transformer are often in a single enclosure. And so you might not get two separate boxes. You might just get one box, has both of them. The other technology, which is also quite old, is alternating current. As the name implies, essentially what it does is takes the AC, which is the wall power is always alternating. So we take the AC power from the wall, put it through a transformer, convert it from high voltage, low current to low voltage, high current, and provide it to the power supply, provide to the parts being welded. There are three different control settings, which are open loop. The first is a tap setting. You can control how much is the maximum current will flow out of the transformer by setting the tap. It can be either directly a knob on the transformer, or it could be hardwired. You can also have some slightly more finesse control by controlling the percent heat. That is a way of chopping away some of that energy in each half cycle. So for example, showing here schematically, if you say you want 80% heat, that means the power supply will chop off about 20% of that half cycle and only send 80% of the energy to the parts being welded. And that can be replicated for each of the half cycles. So if you have two cycles with 80% heat, this is what it's going to look like. Then you can also control the number of cycles. Some power supplies allow you to send just a half a cycle, and all of them will allow somewhere between 1 and the max capacity based on the rating of the transformer. So these are open loop controls. That means you are not directly controlling the current in the secondary loop. You are setting the tap, setting percent heat, and setting number of cycles, but you're not know exactly how much current is going to be in the secondary loop. There are newer AC power supplies which let you do that. You can actually program. You can say we want 10 kiloamps in the secondary, and that's how they work. So you have two choices: open loop or secondary control. Direct current is another technology where the output actually comes out almost, it's like a linear DC. Essentially, it will look like the energy is coming out of a battery. So you can control and program rise time, weld time, and down time, downslope. And this is what it will look like on an oscilloscope. You also can control whether the output is controlled by current, or you're controlling the output voltage at the electrodes, or controlling the output power. So these are three different choices. DC power supplies can be two different types: rectified DC, which is connected to a three-phase input. And so it can produce more welds per unit time. So you have a higher rate of welding. Linear DC is actually a stored energy type power supply. So where you are storing the energy, again, in a capacitor bank, but instead of discharging it like in an open loop environment, in this case, you discharge it in a controlled manner. So you can actually get a certain profile on the oscilloscope or the monitor. So both DC, rectified DC, and linear DC have secondary loop control. And these units are usually small, so the power supply and transformer are often in the same enclosure. Direct current power supplies are limited to lower values of energy. So if you want a higher level of energy, but similar performance as DC, you have the choice of going to high-frequency inverters. The high-frequency inverter is a technology which takes energy from the wall, rectifies it, and chops it into pulses. And each pulse is based on the frequency of these pulses based on the frequency that the power supply is set up for. And the width of each pulse will essentially control the energy in the secondary. So narrow width means low energy, higher width means higher energy. Here again, we can control the output in all forms of control modes, voltage, current, or power. And the frequency of these square pulses will depend on the unit. So the larger units, which can go up to 30, 40 kiloamps, usually are regulated at 1 kilohertz. That means there is one pulse per millisecond. The smaller units usually can go up to 25 kilohertz. That means there are 25 of these pulses in 1 millisecond. The output from the primary looks something like this on the top screen, top chart over here. And when this goes through the transformer, there is a step up in the current. At the same time, the profile starts looking something like this, as shown on the screen over here. So this comes closer and closer to a DC profile. When you have a 25 kilohertz inverter, this almost resembles a DC with a very minor perturbation on there. HF inverters, as I mentioned earlier, can have the choice of primary control, but it is not very common, but you can get units with that. All of them will have secondary current control, where you can actually control this energy in the secondary, whether it's current, voltage, or power. So you have 4 different types of power supplies: AC, DC, cap discharge, and HF inverter. That's a very unique aspect of resistance welding. Provides you a very wide range of choices so that you can have exactly the type of power supply you need for a certain application. Here I'm showing you a power supply comparison of all the 4. The first 2, AC and DC, are the oldest technologies out there. AC, alternating current, operates in cycles. So the typical cycle time will be somewhere between half cycle to 20 cycle. It is very rugged and inexpensive, lasts you for a long time. However, there is poor control at short cycle times, and in some situations, you're using it in open loop, and that also does not have a lot of control. CD or capacitor discharge are for shorter welds, short as a millisecond or 2, up to about 20 milliseconds. Again, very rugged and inexpensive. Again, with limited control capability, because all CD power supplies operate in open loop. So you're not controlling the absolute value of the current. You're just sending the energy through the transformer into the secondary, and the result is based on the secondary impedance as well as the resistance of the parts you're trying to weld. The 2 technologies which have come up in the last quite a few years, quite a few decades actually, is the high-frequency inverter and DC. The high-frequency inverter, again, of the order of milliseconds, say 1 to 200, a typical cycle time usually is about, say, 20, 30, 40 milliseconds. Very similar to DC in performance, but it can be made to have very high currents. So you can get a high-frequency inverter power supply that can go up to 30, 40 kiloamps. Of course, it's higher technology and it's quite expensive, but it provides all the facilities you need to control the energy going out to the weld. DC or direct current is a very pure way of sending out the energy, very precise, very down to a few milliseconds, even perfectly controlled to a few amps in the range of. So usually 0.1 to 50 milliseconds, but I would say typically for medical devices would be of the order of 4 to 10 milliseconds. I have made welds with a DC power supply down to 25 amps. But again, the more common range would be, say, 100 to 500 amps for medical devices and slightly more for other applications. It provides excellent controls for welding of thin foils and small wires. Of course, it is expensive. Usually has low duty cycles, but this is probably the most precise of all the power supplies, and hence is very, very common in the medical device field. Well, I want to thank you for your time and your interest in this video on power supplies for resistance welding. There are other videos in the resistance welding playlist that also might be of interest to you, including bond formation resistance welding and projection welding and parallel gap welding. So if you're interested, please review those. And again, subscribe to this channel so that next time I post a new video, you will be notified. I want to thank you for your time and enjoy your experiences with welding. Take care.